this, yeah, you have to go in there and,
What do you do your shear go?
yeah, we'll just look at it. So we got these two here, right? And the trick here is they're just supported over here in this one corner. You know, it's a cantilever beam. So that's the only trick. Yeah, get it to cooperate now. There we go. Okay, so to find out what's going on here at let's see, maybe it'd be better if I move this over a little bit towards the middle. Okay, so to find out what's going on here, we'll call this A in both cases, so that's AY. Find A, we just sum the forces into Y. We have minus 10 plus, or minus 3 kips per foot over 16 feet, so that ends up being 48. So there's another 48 kips here. Plus AY. So AY equals 58 kips. So that's essentially that's what's going on. That's the max shear there, isn't it? 58. So what you need to do on this, in this example, is go in there and look at this thing at 8 feet. And look to the left of it. We kind of alluded to these the other day, didn't we? And what's going on to the left of it? So if we draw a free body diagram of just to the, yeah, let me put that where it belongs. At 8 feet, if we just draw a free body diagram of what's going on there. So if we're looking at this, and we're just to the left of it, let's see, get that out of there. The only thing we have to concern ourselves with is one force right here. Now we know this overall is 8 feet. This area in here is 4 feet, isn't it? Okay. And that force is 24 kips. Right? It's 3 kips per feet over 8 feet. And that's why it's in the middle there. That's that concentrated load, or excuse me, evenly distributed load. So at that position, the shear is what? 24 kips. Positive, right? The moment at that location is 24 kips times 4 feet. So 96 pounds-feet. Now that's looking at it from the left side of that force, basically, right, at the 10 kips. If we look at it at 8 feet to the right, well, what do we have then? We've got that 24 kips still. But we also have to account for that 10 kips, don't we? So this is still 8 feet, and that's still 4 feet. So the shear at that point over to the right is the 24, and that's actually minus, isn't it? Well, yeah, it doesn't. It's 24 plus 10, so it's 34 kips going down, right? Positive. Or is it? Let's see. Yeah, I got it, yeah. The moment there now is still 24 times 4, isn't it? because you can't take the 10 because there's no distance. Here are the keys. These are the things that we're really looking for there. At that reaction where that 10 kips is added in, we need this V value right here, this shear value, and that shear value right there to be able to make our shear diagram. Okay? So to do that, so the moment really wasn't that critical. But the shear diagram then,
I just have a quick question.
okay?
Is it 96 pounds or 96 kips?
Oh, kips. Yeah, yeah, thank you. Not fair to change the units right in the middle, is it? I guess it is if you put the right values. Do what?
I just didn't know why we changed the units, so that's
No.
why I was asking.
It's kips feet.
Alright.
We did because I wasn't paying attention. And actually, I did it on this paper too.
Oh,
On that,
on your
yeah,
phone.
that I scanned for you guys. So be careful. I did the same thing there. I better mark that so I can fix it. Sure did. Well, and I even did it on the moment on one of the other ones. Brain dead. Okay, so on the shear diagram now, so what's happening is we start out here at 0. Then it looks like we go to 24. So we go in there. Nothing changes till we get to that force, and that's 24. Then it goes down 10 more, doesn't it? Based on that 10 kip force there. So it goes to minus 34. Well, what was it out on the end? Out on the end, it was 58, wasn't it? So then this goes to 58. And then that, it's an evenly distributed load, right? So it's evenly distributed load. Well, let's see. Now that's interesting. That probably should be an arc, shouldn't it? Yeah, those two should be arcs, shouldn't they?
The arcs only come into play on the diagram. Is that not right?
Yeah, yeah. Then that's what I show here. Yeah. Now then, okay. So now if I go and figure out the what I did on mine was I put a little dash in there, so I can figure out the areas of those 3 regions. This 24 times what, 8 divided by 2, 96. 34 times 8, 272. And 58 times, or excuse me, what was that?
34 minus 58.
Well, it's what, 14? 14 times 8 divided by 2, 96. Okay, then I'll draw my, oh, and that was 0 there and 0 there. I'll draw my moment diagram now. Okay, at this point right here, it's 96. At this point right here, it is, bless you, minus 464. So you get an arc there, a terrible arc, and an arc there, because they are that evenly distributed load. Mm-hmm. Okay. You got to do the moment, you add these areas, right? So it started at 0. Then you add the 96. So that gets you to 96. Then you go from there. You have to add these other two areas in there. Now they're negatives. They're all negatives, okay? So it's 96, if you will, plus, this is negative 96 plus a negative 272 minus 96. And then that should equal 464. Negative 464. Okay? And they're arcs because they're evenly distributed loads. And also note, when you get this 464, if you go back to the very beginning when we found our forces in the y, if you did, I can find my cursor. If you did a moment at, let's say, the right side, and you set that, you've got what? Let's see, make sure I'm looking at the right one here. 58 times 8. That's this total right here, times 8. That's it, right? Multiply that out, it's 464. Okay, which just so happens to be what we got there. So it's a way to check to make sure you got what you need. Okay? So the shear diagram helps you find this moment diagram, which also tells you if your moment is right up at the top, or if this is right at the bottom, however you want to look at it. Let's see, I gotta get rid of this though, don't I?